Hello everyone and welcome to this video on how to run an exploratory factor analysis in the free JASP software. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. Usually I talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources including workshops that I teach for QuantFish. In this video, I want to share with you knowledge about how to run an exploratory factor analysis for free in the very convenient, very user-friendly JASP program that you can download from the internet, that is super intuitive and makes it very, very easy to run exploratory factor analysis, confirmatory factor analysis, and lots of other statistical analyses, including t-tests, analysis of variance, regression analysis, power analysis, and others. So here you can see what the user interface looks like after you install JASP and you open the program. And so the first thing that we want to do is open a data file that we want to use for our analysis. And JASP is great also in that it allows you to directly open, for example, SPSS files. So here I have a data file that's called math.sav that I'm going to open. You can also open other types of files. So you could open, for example, text files or others. So I'm going to use an SPSS file here, but that's not the only option that you have. You can see it loaded my data file here from SPSS, and now I am free to choose from the point and click menu at the top, which I find very easy to use, very intuitive. So you can see here's all kinds of stuff: descriptives, t-tests, ANOVA, mixed models, regression, frequencies, and then factor. And so when you click on factor, you can find first of all principal component analysis, PCA, and then exploratory factor analysis and confirmatory factor analysis. I have a separate video on this channel where I show how you can use JASP very conveniently for running a confirmatory factor analysis. So if that's what you want to do, then check out that other video, for which you can find the link in the description. Today we want to do exploratory factor analysis, so we're going to choose the second option from the top. And so now you can see in JASP you have always on the left-hand side your choice of variables from your data set plus the different options that you can choose from for running your analysis. And on the right-hand side you have your interactive results window where the results will be automatically displayed once you click on an option on the left-hand side. So the first thing that we want to do obviously is we want to select our variables for which we're going to run our factor model. And so I'm going to pick the first three variables from my list. Those are three subscales from a cognitive abilities test. And then I'm also going to choose MRT1 and MRT2, which are two test halves of a mental rotations spatial ability test. And then I'm also going to select four subtests from a math scale, from a math test. And so I want to run an exploratory factor analysis for these variables to see how many factors I need and how they are to be interpreted. And you can see that already JASP has generated some output on the right hand side in the interactive output window. And so one thing that is nice about JASP is that the output on the right hand side changes as soon as you select additional options on the left or other options on the left. So it automatically makes those adjustments to your output, so you don't have to rerun your analysis a million times when you notice, oh, that's not what I wanted, oh, that's not the maybe number of factors that I wanted, or maybe that's not the rotation method that I wanted. And then you have to go back, like in SPSS, for example, you would have to rerun everything over and over and over. And so here you don't have to do that. You just click on the left and then your output on the right hand side will change accordingly. Let's take a look at the options on the left-hand side to see what we can get there, what maybe we haven't gotten yet, and what we actually want. So on the left-hand side, you can see that one important issue in factor analysis is the number of factors to retain, and JASP offers different options for doing that. The first one is parallel analysis. In parallel analysis, you compare the eigenvalues of your actual correlation matrix for the real data to the eigenvalues that are obtained from an analysis of random data, specifically multiple replications or multiple runs of an analysis of eigenvalues from random data that should not have any meaningful correlations. And then the eigenvalue plot, the scree plot for the real data, is compared to the scree plot for the random data, and then we can see how many eigenvalues for the real data are above the intersection with the scree plot for the random data. And so you have a choice here between doing that for principal components or factors. The parallel analysis, you also can choose the seed, meaning the random start number that you want to use to run this analysis. It really doesn't matter that much which number you choose here. So we're just going to leave it at 1, 2, 3, 4. And then another criterion or option is to choose factors whose eigenvalues are greater than 1, meaning retaining as many factors as there are eigenvalues greater than 1. That's also called the Geiser criterion, and that typically leads to too many factors, so parallel analysis is considered a better method for selecting the number of factors. So we're going to go with that for now. Another option is to select manually how many factors you want to retain. If you already have hypotheses about how many factors you think should be extracted, then you can also set the number of factors manually and then inspect the solution with a fixed number of factors. Below that is the method for extracting factors, and so when you click on this drop-down menu, you can see there are a bunch of different options for how to do the estimation. And so one popular option is maximum likelihood factor analysis. Another one would be principal access factoring and others. So let's do a maximum likelihood factor analysis here for this example using maximum likelihood estimation. On the right-hand side, you have different rotation methods for rotating your factor solution. The default is oblique rotation. Oblique means after a rotation, the factors will be allowed or are allowed to be correlated, so they are not forced to be uncorrelated, which would be the case with an orthogonal rotation. That's an orthogonal rotation that's typically not realistic because usually factors are correlated at least to a certain extent, so oblique is probably what you would want in most cases, and the default oblique rotation method that is used is Promax. There are other methods as well that you could choose from in the drop-down menu. The analysis is based on the correlation matrix. You could use the covariance matrix, or for ordinal data, if you had ordinal or binary variables, you could use polychoric or tetrachoric correlations, which would be appropriate for binary and ordinal items. And that's actually great that JASP has this option that allows you to use the proper correlations for binary and ordinal data. Many statistics programs do not have this option, so that's really fantastic that they also have proper methods here implemented for binary and ordinal data. We can also click on output options to display additional output and make sure that what is output is what we want. The default here is that only factor loadings of 0.4 or greater will be displayed, and that's actually something that I don't like. So I personally want to see all the loadings. I don't want to suppress small loadings because even a cross loading of 0.38 could be meaningful. So I want to see it, I want to see what's there, and I therefore would prefer to set this to 0 by going down here from 0.4 to 0, so that all loadings will be displayed, even ones that are 0 or only slightly above 0. The factor loadings will be ordered by factor size by default, or you could order them according to the variables. So I don't care right now, so I'm going to leave it at that option here. Also, you can request additional output tables. For example, one thing that we definitely want to look at are the factor correlations. So we would definitely want to know how strongly our factors are correlated in the solution. So I'm going to choose that. Since this is an oblique rotation, we will have correlated factors, and so we want to study how strongly those factors are correlated. Also, it maybe doesn't hurt to look at additional fit indices for the solution, and then we want to see the results of the parallel analysis. Here we're going to use the parallel analysis based on principal components. And then we can in addition obtain a path diagram of our model as well as a scree plot with the parallel analysis results. So that's really nice, because that way we can form our own opinion about the scree plot, and maybe we would interpret the scree plot per se, because that's also a criterion for factor selection, is simply looking at what the scree plot looks like and whether there's a clear drop in, or where a place where the scree plot becomes flatter. So that's also something that we might consider. So it's a good thing that we can also look at that. When we click on the right hand side, then JASP will update our output if it hasn't already done so by or for the things that we clicked on the left hand side. So now this has been updated, and you can see that the first thing that JASP outputs is a chi-square test of model fit for the maximum likelihood factor analysis. And that's one advantage of a maximum likelihood factor analysis, that we get a chi-square test of model fit that tests whether the model adequately reproduces our correlation matrix that we observed. And you can see actually this model that JASP retained here does not fit the data adequately according to the chi-square. The chi-square value is 94 with 19 degrees of freedom, and it's highly statistically significant. The p-value is smaller than 0.001, so the null hypothesis of exact model fit is rejected or can be rejected. So in other words, the model does not fit the data. Now, what model did JASP fit here? Apparently a two-factor model. You can see that from the factor loading matrix, where the factor loading matrix here contains factor loadings for only two factors, factor 1 and factor 2. And so this means a two-factor solution must have been retained. Now, what does it look like? You can see that factor 1, with the loadings sorted according to size, primarily loads the math variables. So the math variables are the highest loading variables here on this factor. So this is sort of like a math factor. However, also the variables of the cognitive ability test, KFT, also load on this factor with loadings above 0.6. What does not load on this factor are the mental rotations test halves. So MRT1 and MRT2 have loadings very close to 0 on factor 1. So this is like sort of like a cognitive abilities general factor, except for spatial ability, because it captures math ability and then also those other cognitive ability reasoning subscales. The second factor then is a pure mental rotations factor. You can see the mental rotations test halves load strongly on that factor, and the only other variable that loads somewhat substantially, not really, but somewhat substantially on this factor is the figural subscale of the cognitive abilities test, which makes sense because that uses abstract symbols in the same way as the mental rotations test. So it kind of makes sense that that variable would load a little bit or cross-load a little bit on factor 2 as well, but it's not really that dramatic, 0.167. So looks like this two-factor solution would have a decent interpretation. However, we saw earlier from the chi-square test that it didn't fit very well. So we might explore other solutions as well. Let's go down a little bit and take a look at the other output. In the next table, we get a summary of the unrotated and rotated solutions in terms of eigenvalues, sums of squared loadings, proportion of variance, and other indices. But for now, I want to focus on the number of factors because we're not even sure that 2 factors is good. So I'm going to go down a little bit more and look at other indices and criteria for factor retention. You can see the factor correlation between those 2 factors is about 0.4, so it's a medium size. They are positively related, not super strongly, but they are substantially correlated. So in other words, an orthogonal rotation here definitely wouldn't make sense. If you find a factor correlation of 0.4, that's fairly substantial. So let's go down, let's take a look at the eigenvalues. So here you can see the real data component eigenvalues, and you can see that there are 2 above 1. So the Geiser criterion would also result in a 2-factor solution because there are 2 eigenvalues above 1 in the real data where they are marked with a star saying factor should be retained according to that criterion. In the right column, you can see the simulated data mean eigenvalues. So those are the eigenvalues that are obtained from a simulation of random data that shouldn't be correlated above chance. And so this is then averaged across multiple runs or multiple draws of random data. And you can see there are quite a few also that have eigenvalues greater than 1. In this case here, 5 components have eigenvalues greater than 1. And we can compare those sets of eigenvalues for the real data to the set of eigenvalues for the simulated data of random variables, and we find that as a graphical display in the scree plot, at the very end. So the scree plot here has the eigenvalues for real data right here, with a characteristic initial steep decline in eigenvalues and then a pretty flat rest of the distribution. You can see that according to this criterion, we would retain 2 or 3 factors when we look at the scree plot, because right here after the 3rd factor is where things level off. And so I would say actually 3 factors to me would make more sense in terms of the pure interpretation of the scree plot itself without the parallel analysis, because I find that we should go with the last factor here and then the other ones are in a straight line. But that's pretty subjective. Another person would say, oh no, drop the 3rd factor. The parallel analysis also points to there being only 2 factors. You can see the intersection between the parallel analysis eigenvalue distribution, which is very flat, and the real data eigenvalues is right here. And so according to that parallel analysis criterion, we would retain the factors that are above this intersection right here, which would be those 2. And the eigenvalue greater than 1 criterion is also included in the plot, in that we have this horizontal line right here at 1, so that we can also easily see which eigenvalues are above 1 in the real data. So in summary, the parallel analysis and the Geiser criterion would point to there being 2 factors. The chi-square test indicates that that may not be enough. So I would then also, what I would do is I would go and take a look at a 3-factor solution as well. And we'll do that in a moment to see what that solution would look like. Before we do that, let's take a quick look at our path diagram here, which nicely illustrates the strength of the loadings. So in a graphical way, you can then clearly see, oh yeah, the factor RC2 here is a mental rotations factor. Here are the strong loadings, and there's only one relatively sizable cross-loading. That was the one cross-loading of the figural subscale of the cognitive abilities test. But really this factor is pretty much purely a mental rotations factor. Whereas the RC1 factor here loads the math variables and also all of the cognitive ability test subscales, where the strongest loading is for math 3. Now let's check out a solution that has 3 factors, and we can do this very easily by going back to the left-hand side, clicking on manual and choosing as the number of factors 3. And then you'll see that the output on the right-hand side automatically adjusts to that change in the input. So we're not getting, so say, everything again, but instead our solution is changed automatically to a 3-factor solution. And now the chi-square test is much lower. So you can see it's only about 12 degrees of freedom. It's still statistically significant. So even a 3-factor solution does not have a perfect fit in this example. But let's take a look at it nonetheless and see what we get for the 3-factor solution. So what does that look like? You can see that the factor loadings now look such that the math variables all load on factor 1, and then nothing else except for the cognitive abilities quantitative scale, which totally makes sense because that uses numeric material, numbers, and therefore it makes sense that that groups, or that also loads at least a little bit on factor 1. You can see that cross-loading is 0.307, so it's not a dramatically high loading, but definitely there's some aspect that is shared between this scale and the math factor. The other variables don't load on this factor. Really, those other loadings are very close to 0. Factor 2 then is one that is defined by the remaining cognitive ability scale variables, figural and verbal. You can see those loadings are 0.71 and 0.79. And then also the quantitative scale of the same test has a loading of 0.41. So that scale is a little bit in between factor 1 and factor 2, which makes sense because it uses numeric material. The third factor, again, is then a mental rotations factor. So that is clearly separate from the other variables, because you can see the MRT1 and MRT2 variables really have no substantial loadings on factor 1 and factor 2, but they do have substantial loadings on factor 3, and then also none of the other variables now have any substantial loading on factor 3. So factor 3 is most clearly defined in terms of mental rotation. Factor 2 is relatively clearly defined as a cognitive ability test factor, and factor 1 is a math or numeric material factor that is primarily defined by the subscales of that math test. Going down, we find the factor correlations, and interestingly, factor 1 and factor 2 are strongly correlated, 0.77. So the math factor and the cognitive ability factor are strongly related, whereas both of these factors are not so strongly related to the mental rotations factor, 0.33 and 0.42. So again, factor 3, the mental rotations factor, is most clearly distinguishable from those other two factors. You can see the RMSEA fit index looks good for this model. Also the SRMR 0.015, the TLI and CFI, which are all classical indices for maximum likelihood factor analysis and structural equation modeling, they all look good. So we could say, well, it looks like the 3-factor model may be better than the 2-factor model because those indices are better, and there is a difference between the math variables and the cognitive ability test variables, even though they are closely linked, but maybe they should be split out across 2 separate factors rather than being on the same factor. The path diagram then is also adjusted to that 3-factor solution. You can see that now we have 3 factors, obviously, and again we have the clearly defined 3rd factor for mental rotation. We have a relatively clearly defined factor RC2 for the variables of the cognitive ability test, and we have also a clear numeric / math factor, which primarily is defined by the math variables. The scree plot obviously is the same as before, with the eigenvalues for the actual data and the simulated data. So you can see it's really straightforward to run such an EFA in JASP. You have a lot of options, you have a lot of nice tools to study your factor solutions, select the number of factors, and visualize your factors in this software, which I really like. And also one thing that I want to point out here is that at the top there's a little button, show info for this analysis, and this is actually really useful. When you click on that, you can find a lot of additional explanations about the assumptions of that analysis, about how to select the number of factors, the factor method and rotation method, as well as many other pieces of information. At the very end, you can find references, so papers with links even, and so also there are different packages listed for the R software that you can use for factor analysis. So it's really, really well documented and very helpful to use this program for an EFA. I hope you found this video useful to learn about how to run an exploratory analysis for free in the completely freely downloadable software JASP. If you did, please subscribe to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.